Hello, assalamu alaikum. My name is Hasib and I am from AIUB. This presentation is for microprocessor and embedded system course. My ID is 183693991 and this is for my midterm assessment. So let's dive into my presentation. So the chapter 1 is introduction to microprocessor and microprocessor based application. Microprocessor used 4 data types: unsigned and signed binary integers, BCD numbers, ASCII and floating point numbers. So what is unsigned and signed numbers? Unsigned and signed number is just represent of basic binary digits which don't have any arithmetic signs, and these numbers are used basically to represent memory addresses and all. And the signed number has an extra bit that represents some arithmetic values, whether it is positive or not. Mostly 0 for positive numbers and 1 for the negative numbers. And the second is BCD, binary coded decimal. There are two forms of binary coded decimals. One is packed and another is unpacked. So unpacked represents each bit as a byte and the packed represents 2 bit as a byte. And the ASCII values are alphanumeric values which represent some special symbols to process data in the microprocessor. The most important part of is floating point number that converts decimal number into some standard floating point number. So let's see how microprocessor converts a decimal number into a floating point number. There are 6 steps to convert a decimal number to a floating point number. Point to be noted that the floating point number will be 32-bit numbers. So at first we have to convert the given number into a binary number. So let's move into our Ziteboard to see how it's calculated. So here I am opening Ziteboard. So I am taking 10 as sample decimal numbers, 2 and its binary is 1010. So we have to make this into 3 components such as sign, exponent and matrica. So let's convert it in this 1.010 into 10 to the power 3. In here this 3 is exponent and this one is matrica and the sign in front of it is plus. This is the sign. And here for positive the sign is 0. So in here this is the exponent and we have to bias the exponent. To bias the exponent we have to add 127 to it. 127 plus 3 is equals to 130. Sorry for my handwriting, this is 130. So now we have to convert this 130 value to 8-bit binary numbers. So if we convert this 130 to the 8-bit binary numbers, what is the output? The output must be 100 and 10 4-bit and another 4-bit 01. Sorry, 0010. This is the representation of 8 bits binary of 130 decimals. So this is our biased component and the sign bit is 0, and the rest 23 bits will be 0 1 0 and 0 1 0 0 and 5 more blocks of 0 of 4 bits. You know the idea. So this is how we represent 10 decimals into floating point number. So let's get back into our slide. So you can see our answer is verified. There are 4 major parts of a CPU microprocessor. The number one is CPU, second one is memory, third one is input output circuit, and fourth is buses. So what is CPU? CPU is consists of some transistors, millions of transistors that process our data. Memory is where the CPU keeps data to process it, and input output circuit is the input output circuitry is like a bridge which brings input from our input port and deliver output to our output ports. There are 3 buses like address bus, data bus, and control buses. There are memory organization. 3 types of memory organization. 1 is processor memory, 2 is primary memory, and 3 is secondary memory. Processor memory is integrated with the microprocessor. We called it cache memory, and the cache memory is high costly and there is no delay in data transfer. Primary memory and main memory represents as RAM and ROM, and the secondary memory is hard disks and other storage devices. So now let's move to the linear main memory array assign. There are 3 types of techniques frequently used. One is linear decoding, partial decoding, and memory decoding using PAL. We can see in the linear memory, it's a way to connect 8-bit microprocessor with 6 kilobyte RAM. The main disadvantage of this linear decoding, it uses some unnecessary chips from the microprocessors, RAM. But in here we can see that partial memories doesn't use some unnecessary chips from the RAM. So let's move into our chapter 2, introduction to I/O, input output. So there are 2 types of I/O devices, like one is physical I/O and one is logical I/O. Logical I/O is more likely some virtual I/O provided by microprocessor to provide some data to execute some operations at microprocessors. The second I/O device is physical I/O. The physical I/O is mostly user inputted I/O devices. User can directly access to the I/O devices to input values and get output from the microprocessors. So physical I/O has 3 parts. There are 3 ways of physical I/Os. One is programmed I/O, one is interrupt driven I/O, and third is direct memory access or DMA. This programmed I/O access via registers. The process is called command or data direction registers or DDR. What's the DDR do? DDR inputs 0 and 1 in the microprocessor. The 0 is for enables the input buffer and the 1 is for enabled the output buffers. Interrupt driven I/O executed by interrupt pins in the microprocessor chips Suppose a program is already running on the microprocessor, meanwhile another input is given, then the interrupt driven IO. This is called the interrupt driven IO, and it executed by interrupt pin. So there are three types of interrupts: external interrupts, internal interrupts, and software interrupts. External interrupts means we execute some process physically, and internal interrupts means some internal process is requesting access to process the data holding the current process, and the software interrupts is some other software requests to process data. Direct memory access is another interrupts, something like direct memory access is another IO. It is controlled by DMA chips, direct memory access chips. What the direct memory access chips do, the request is firstly go to the DMA, then the DMA allocates a process for the requested process, then the current process is halt, the requested process is executed. So the request of process of IO is going to the DMA, it manages by DMA. The DMA may controls the processing in three-way: block transfer, cycle stealing, and interrupt DMA. Cycle stealing means the current process running on microprocessor have some cycle. DMA steals some cycles to from it to run the the interrupted process. Block transfer is to transfer the request block to the microprocessor. And the final chapter 3 is SAP. SAP is simple as possible compute. It is a architecture how microprocessor computes data. To see, we can see we have a program counter, a input, and MAR, and RAM 16x8, instruction register, controller register, accumulator register, adder, and a register called B, output register, and binary display. It has some separate pins to execute their particular jobs. So let's see how this SAP works. We can calculate for example some numbers to simulate the architecture. So let's again move to our Zeta board to have some calculations. So let's erase our previous data from here. So as we can see, there are 6 steps to execute the SAP. The first 3 steps are same for all kind of operation. Rest 4, 5, 6 is different by some different operations. So you can see I already drawed 6 steps in here. So let's calculate 7 minus 5, how it is executed in the SAP architecture. So the 7 is stored in 2H registers in microprocessor, and the 5 is in 4H. So let's see how it is calculated. So in T1 steps we can see LM and EP pins are activated, and the program counter is initiated with a value PC is 0000. This is initial counter value, and we can see the T1 step the PC value will store to the MAR, memory address registers, MAR, Then in T2 steps, the program counter value will incremented by 1, so PC will be 0 0 0 1. So we completed our second steps. So in third steps, so what we are doing at first, we are doing the operation is called LDA to store the first value. So LDA, let's say LDA instruction is stored in 000. So the RAM will store the first 4 bit as the instruction bits 000 4 bits, and the 7 which stores in 2h. The binary representation of 2 is 0 0 1 0. So our third step is completed. So from the RAM, the last 4 bits will go to the instruction registers. In T5, the value in IR is T4. The value in IR is 0010. So in 0010 address, we can see the value is 7, so the value will be registered in MAR, memory address register, which is 8-bit 0000, and 7 will represent by 0111. So our fourth step is completed. In fifth step, from MAR, the value will be stored to the direct accumulated registers. So MAR, the value in MAR is 0000 and 0111, and this will go to the accumulated registers. And the sixth steps, there is no sixth step, so the sixth steps will be none. Okay, so we can see we successfully stored this value in our registers. So now we had to subtract 5 from 7. So let's see how it's done. Let's erase our board. Clear all. So the sixth step, as I said, the first 3 steps will be same as I did in the first operation. For the subtraction, we follow this T4, T5 and T6 for the subtraction. So 41, the PC, so the PC was incremented in the first operation. The value was 0001 after increment. So the incremented value will be registered to MAR. For this operation, again the program counter value will be incremented by 2 1 0. And in third step, RAM. So let's say we put subtraction instruction as 0 0 1 1, and from the our 5 was this value 5 was stored in 4h. So converting 4 into binary, the value will be 0 1 0 0. This 4-bit values, so these 8-bit values will be stored in the RAM. This is our T3 steps. And from RAM, memory address registers will go to the address and take the value. So in 4H address we can see the value is 5. So the in the memory address register the value will be stored as 8-bit, and 5 will be stored in binary 0 1 0 1. So this is 8-bit representation of 5 in where MAR, in MAR. Okay, so our T3 steps is completed. So as we recall our memory, we stored this value in accumulated registers in LDA operation, but in subtraction operation we will store this value to the register B. So MAR values sorry, I did a mistake. In step T3, the last 4 digit will be go to the instruction registers. From the instruction registers T4, the value from 4H 5 in 8 bits binary will be go to the MAR. So in T5 MAR values from MAR will be stored on B registers, and in T6 our previously stored value in SCC. From SCC our recent stored value V will be abstracted. So our previously stored value was value was 0 0 0 and 0 1 1 1. Subtract, let's divide, subtract B we stored in B register, which is 0 0 0 0 and 0 1 0 1, and the output will be 2 in decimal. Okay, this is the full calculation of how SAP works. So this is the end of my presentations. Thank you